Okay. Well, thanks so much for inviting me to this. Maybe this is sort of backwards, but this is the first time I've presented this. I wrote the paper before I presented it. So hopefully there aren't any glaring errors that I would have caught if I'd given this as a talk before. But if there are, maybe we'll learn something. Okay, so yeah, this paper is about how I think that structural representation and analog representation are just the same thing. There are two names for the same type of representation. So, a general project that I think is kind of interesting is trying to decide what types of representations there are. And there are a bunch of different ways that we could try to classify or categorize representations. We could try something like, maybe we can distinguish natural and artificial representations, or maybe we can separate them based on, what kind of content they have, or, where the content comes from. Is it original content versus derived content? Maybe we can separate things based on the format. There's some words people use like iconic and structural and propositional and digital and analog, etc. Maybe we can separate discrete representations from continuous representations. I don't know which of these are viable or more viable than others, but this is in general a kind of addition to that project of trying to figure out what types of representation there are. And so, like I said, the main idea is just that structural representation and analog representation are the same kind of thing. Why? So examples of analog representation are typically one-dimensional, and we'll look at a lot of examples because I think it's a lot easier to understand what's going on when we look at examples. But things like liquid thermometers and analog clocks, those are the kinds of things that we typically think of as analog representations. And I'll say more about what I mean by one-dimensional. It's maybe obvious, we have one thing that's varying, like with liquid thermometers, the liquid is going up and down. With analog clocks, the hands are moving. But there are other analog representations that are multidimensional, things like maps and photographs or scale models, where there's more than one dimension, right? So I was earlier interested in seeing, I had an idea of how to understand analog representation and extending this analysis of what was originally one-dimensional analog representation to these multidimensional cases results in a characterization that I think just captures structural representation entirely without any remainder at all. So that's what this is really about. So here's what I'll do, or try to do anyway. So I'm going to sketch this analysis of analog representation and then show how to extend it to multiple dimensions. And then hopefully show that this resulting characterization covers structural representation, and for good reason. This isn't like an ad hoc kind of thing. There are principled reasons why this turns out the way that it does. And then if there's time at the end, I'll address some issues that I think this identification helps clarify. One quick preliminary note. Nothing that follows is a theory of representation. That's a really hard project, and it's too hard for me. So I'm not going to tell you what makes something a representation in the first place. But this is a theory of particular types of representation. What that means is that given that something is a representation, I can tell you about whether it's structural and analog and why, the reasons why. But I'm not going to be able to tell you what makes something a representation in the first place. That to me is an independent project. And I think that that's important to separate those projects, separate the project, the basic project of what is it for something to be a representation at all, from what kinds of representations are there, right? The first project is obviously really important. I don't know if we're going to have a unified answer to that, but I'm setting that aside and just saying, basically, you give me a representation and I can tell you something about whether it's structural or analog, but I'm not going to tell you whether it's a representation in the first place. That's an independent thing. Okay, so some basic analog representations. An analog clock and a liquid thermometer. What makes these analog, at least according to me? Um, these are some symbols. I don't like using symbols when we don't have to, but this is a formalization that is kind of useful. But for a talk like this, I'll throw it up there and then we'll talk about what it means in English. So I think that there are three important things. If you've got some representation and you want to claim that it's analog, well, there's going to be some property of that representation where the amount or the quantity or the magnitude of that property specifies the amount or quantity or magnitude of what it's representing. And the amount, quantity, magnitude of that property that's doing the representing, it's going to be, fancy words, monotonic function of the amount, quantity, magnitude of what it's representing. And that's a homomorphism. It's structure preserving. And this is an important clause, and we'll see why in a minute, but it's a mouthful. An increase or decrease in the representing property does reflect an increase or decrease in what it's representing, but the converse might not be true. So I'll set that aside for the moment, and we'll just look at an example because that's a little bit difficult to explain without an example. So example, we've got the liquid thermometer, right? So we have this representation, it's a thermometer. There's a property, it's that liquid height. Sometimes it's mercury, sometimes it's alcohol. And what it's representing is temperature, right? Very straightforward. An increase in the liquid height reflects an increase in the temperature, and a decrease in the liquid height reflects a decrease in the temperature, right? And increase and decrease here are literal, right? These are magnitudes, and that's an important point that we'll come back to. But literally, an increase in the height reflects a literal increase in the temperature, right? So what about the clock? Well, here the representation is the clock. Let's just focus on the second hand, makes things simpler. The representation is the angle of the second hand, right? So an increase in the angle reflects an increase in elapsed time. And normally in these clocks, we have these digits to make them easier to read, but I'm sure everyone's seen analog clocks that don't have any markings at all, right? The markings are not essential. So that third clause, it's a mouthful. Here's why this is important. This clock could tick in discrete steps, right? And time could increase, but that might not be reflected by an increase in the angle of the hand, right? So if a few milliseconds have gone by, the clock might not have ticked yet, right? However, if the clock does tick, if that angle increases, that definitely reflects an increase in the amount of time. This is important. It's a kind of small technical point, but it's important because we want to get the relationship between the representation and what it represents right. And a lot of times people will say there's a one-to-one mapping, and that can't be true. That doesn't always work. And this is a really simple example of why. So again, we'll come back to this later, but I don't know what units of time there are. Maybe time is continuous, maybe it's very, very small Planck lengths or something the physicists can tell us. Whatever they are, there's a whole lot more of them than there are seconds in a ticking analog clock, right? So that third clause is just to say, look, sometimes what is being represented can increase, but our representation might not reflect that because it basically has a certain resolution, right? But if the representation does increase, that definitely reflects that what's being represented has increased. Okay, so those are the simple examples. Covering them takes a little bit more fancy footwork than one might have thought, but I think this covers these cases pretty well. So now I'll talk about structures and relations, because this is where we can really see the connection between analog representation and structural representations. So just thinking about the thermometer case, temperatures and heights have a structure. Their magnitudes are just ordered by a less than relation, right, or a greater than relation. Very straightforward, right? And in the analog thermometer, there is a structure preserving morphism. We just have this mapping from temperatures to heights, right? So we have the structure in the temperatures. One temperature is less than another, and take all the temperatures and you can order them. Same thing for heights, right? So that's the essence of what an analog representation is, right? We have a structure in what we're representing. We have a structure in the representation, and there's a mapping from the one to the other, right? And that structure is preserved, right? Okay, but one thing is, if you're a philosopher, then you think of weird examples and you say, well, look, relations are really cheap. I can just make something up and say, oh, look, here's a relation between temperatures that I've decided that 6 degrees is this weird less than relation to -2 degrees, and that's this weird less than relation to 17 degrees, right? It's not a natural relationship. I'm just stipulating there is a relation. And we can do that. We can just stipulate relations among all kinds of things. And we can stipulate a different relation among heights and just say that 12 centimeters is the other weird less than to 7, which is the other weird less than to 23. There's just an arbitrary relation that I just completely made up, right? And moreover, mappings are cheap, so I could just map these, right? I could just say, okay, well, I'm going to represent 6 degrees by 12 centimeters, and I'll represent -2 degrees by 7 centimeters, and I'll represent 17 degrees by 23 centimeters. And look, I'm preserving this relation. I have this weird relation among temperatures. I have a weird relation among heights, and I'm preserving the relation. So why shouldn't that count as an analog representation? We have a structure preserving map, but if this counts, then all kinds of things are going to count because I just made that relation up, and you can make up whatever relation you want, right? So it seems like something's gone wrong. But I think the answer is pretty straightforward and simple. When we're talking about magnitudes, there is an inherent relation in magnitudes because they're magnitudes. Any particular magnitude forms a totally ordered group just by the less than relation or the greater than relation, right? They're equivalent. That's what you might call a natural relation. That's a vexed term if you're a philosopher, but this is what you get when you're talking about magnitudes. Magnitudes are what they are in virtue of the fact that they have a size that's comparable to other things of that same type, right? So it's just a case that what it is for something to be 2 centimeters is that it has a length or height that's greater than 1 centimeter, right? So that's the relation that's important, right? And that's not a stipulated or arbitrary relation. And once we have this, to be sure, there are still very many mappings that we could make. But importantly, for this to be an analog representation, we have to use the ones that are structure preserving. And not all of them are going to preserve the structure, but some of them will. So, for example, one thing we can do is just shift things around. We can say, okay, well, we're going to represent 0 degrees by 1 centimeter and 1 degree by 2 centimeters, right? That would still be an analog representation because we're still preserving structure. Or we could flip things around. I don't know why one would do this, but we could say, okay, we're going to have a kind of inverse thermometer, if we could invent such a thing, where as the temperature goes up, the height goes down, right? Okay, we're still preserving structure. This is a weird example, but other examples are not so weird. So for example, timers could work like this. You could have a timer that counts up like a stopwatch or a timer that counts down, right? And what's happening is time is increasing, but angle is increasing or decreasing, structure is being preserved, right? So as long as the structures, of the representation and what's represented are of this less than or greater than relation, and it's among magnitudes, then any structure preserving map will do. Even though there's lots of them, um, any of those will count as an analog representation. Okay, so far so good, I hope. So let's talk about multidimensional analog representations. So part of the characterization of analog representation that I said earlier, I just very quickly glossed over this, is I said an increase or decrease in the magnitude of the represented property, like temperature, is reflected by an increase or decrease in the magnitude of the representing property, right? The height of the liquid. That sounds fine. So again, temperature increase is reflected by an increase in the liquid height. But increase with respect to what? Like what is increasing, right? With respect to what is the temperature or the height increasing? Well, with a thermometer, it's obvious. The increase or decrease is with respect to time, right? Pick a point where you're measuring the temperature of something. As time goes on, the temperature will increase or decrease, and so will the height of the liquid. That will increase or decrease with respect to time, right? That's very straightforward. But what about static analog representations like photographs, like this picture of Margaret Hamilton? Oh, by the way, quick sidebar. This is Margaret Hamilton. She was, if you don't know who she is, she programmed the Apollo guidance computer as part of the US space program. This is a portion of a photograph of her. She's holding a stack of the code that she wrote for this computer. It's really impressive that she wrote all this code. So she was instrumental in getting Americans to the moon on the Apollo program, the Apollo space program. Anyway, static photograph of Margaret Hamilton, right? So obviously they don't increase or decrease at all, right? With a thermometer, the increase or decrease was with respect to time, but photographs don't change, right? So they don't increase or decrease. So what's going on here? It seems like that earlier analysis isn't really going to work, or it needs to be changed or something. Kind of. There is a way in which they do change, but it's not with respect to time. So let's take a minute, and here's the thermometer, right? And we can imagine if we took some measurements of some environment where the temperature is, oscillating sort of rapidly, we could graph the temperature. That's the top graph in degrees Celsius. And then the bottom graph, the red one, is the height of the liquid in centimeters, right? And these things are just going to track each other. So when we look at it like this, we can think of, we have this independent variable, this independent dimension of variation. This is time, right? So as time changes, these things oscillate together, right? Photograph, we don't have time, but what we do have is space, right? So if we just, to make things simpler, imagine we zoom in on just this little piece of this photograph. The way this is zoomed in, it kind of looks like there's several rows of pixels, but imagine that's just a single row of pixels, right? And I found one that oscillates. What do I mean that it oscillates? I mean that if you look at it from left to right, it's darker, and then it's light, and then dark, and then light, right? And if we were to graph the white levels of the image and the gray levels of the corresponding pixels, they would oscillate in the same way. But here, the independent variable, this independent dimension of variation, it's not with respect to time, right? It's with respect to this left-right orientation. And we could do the same thing with, find another place in the picture going up and down, right? So we still have something that's changing with respect to some independent dimension of variation. It's just time versus space, right? So again, the thermometer has time as an independent dimension of variation. And the photograph has space as an independent dimension of variation. And in this case, it's in 2 dimensions. I don't know of any examples of like a photograph where you would have just one dimension, like a single line of pixels. I mean, I guess maybe there's some examples, but normally there are these two independent dimensions of variation. So the overall analysis of the photograph ends up being the same. We have these structures, and the structures are defined by magnitudes and a map that preserves these structures. So let's make that a little bit more explicit. So on the left, I have this kind of version of like the image that the photograph is of, right? And on the right, this is the photograph itself. So on the left, you can think of however you want to think of the points of light in the image, right? And they have this structure. Some of them are to the left of and above other ones, right? That's just how they are. It's a spatial structure that they have. And in the pixels in the photograph, the way we arrange the pixels, they also have a spatial structure. Some pixels are to the left of others or to the right and above and below others, right? So they both have these magnitude structures, and the arrows are the mapping. I mean, this is blindingly obvious. This is what makes something a photograph of what it is the points in the photograph correspond to the points in the image. And a point in the photograph that's to the left of a different point had better correspond to the same left and right points in the image, right? So we have this mapping. Well, let me back up. We have a structure in the image itself. We have a structure in the photograph, and the mapping from the points in the image to the points in the photograph preserves that structure, right? There's another structure that's preserved too, and that's if we think about each individual point, in this case, it's a black and white photograph where, we say black and white, it's actually grayscale. We have this photograph where the luminosity of the point in the image is reflected by how dark the pixel is, or the point is in the photograph, right? So this is another structure that's preserved. There's a structure among luminosities, some are brighter than others, and gray levels in the pixels, right? So that structure those structures are also preserved by the obvious mapping, right? Okay, that's a lot. I'm hoping the examples made that clear or clearer, but we can extend this idea to further dimensions. It's kind of tedious to do so, but we can think of scale models or animations, things like maps, or complicated things like complex animations of scientific animations where we have a 3D model that's has colors where the colors show the heat of an airplane or something, and the heat changes over time, right? So we can have a whole bunch of different dimensions of variation, but the thing is we can do the same analysis, right? Where we have structures among magnitudes and they're preserved from what's represented to the thing doing the representing. So I'm saying what I just said. The structure of the magnitudes found in the target is preserved by the structure of the magnitudes in the representation, right? And the interesting thing that differs here is just the number and types of independent versus dependent dimensions of variation, right? So we go from a really simple case like the thermometer or the clock, and there the dimensions are so obvious that we normally don't talk about them, but if you do make sense of those dimensions, then you can extend the dimensions to make sense of more complicated cases of analog representation. Right? Okay, so great. So much for analog representation. What about structural representation? So here are some quotations from the philosophy literature. Here's an early one. Structural representation. The pattern of relations among the constituents of the represented phenomenon is mirrored by the pattern of relations among the constituents of the representation itself. Here's a couple newer ones. Structural representation, a mechanism in which a structural correspondence between a set of vehicles and a target domain is used to accomplish a certain task. As a first approximation, structural correspondence refers to some kind of structural similarity between a set of entities and a target domain. Another one more. In the case of structural representations, a vehicle or a system of vehicles must be structurally similar to the target system. Simplifying to the extreme by structural similarity, I have in mind a relation of one-to-one correspondence between at least some of the elements of two distinct domains, such that the same abstract pattern of relations holds between the elements of the two domains involved in the correspondence. In the case at hand, the two domains are representational vehicles on the one hand and targets on the other. So maybe this sounds like what we've just been talking about. And my claim is that in characterizing multidimensional analog representation, we just also characterized structural representation. And there isn't anything more to talk about in terms of structural representation that hasn't already been covered by trying to make sense of this multidimensional analog representation. Because in both cases, what is important is that they use structures, and they use magnitude structures, not just arbitrary or stipulated structures. And specifying that we're talking about magnitudes and the natural ordering of less than or greater than blocks just arbitrary structures counting. And the structures in the target are preserved by the structures in the representation, right? So again, what was true for analog was true for structural representations. So we win, we covered both. Okay, so let me just talk about a few kind of other thoughts since I have a little bit of time here. I do have some time, right, Tobias? Yes, okay. So I kind of mentioned this earlier, but it's important that we use homomorphisms, not isomorphisms. That just means we don't want one-to-one correspondences. That just doesn't work. And so, imagine that the image on the right is the real Mona Lisa, and the one on the left is this, low-res photograph of the Mona Lisa. We've got to have, if we had a one-to-one mapping, well, we're not going to get one because we have way fewer points in the representation than there are on the actual Mona Lisa, right? So we just don't get to have a one-to-one mapping at all. And in fact, it's a little tricky to say, well, maybe we don't need to map all the points on the Mona Lisa. We just need to make sure that each pixel in our photograph is mapped to, some point in the Mona Lisa. Maybe, I'm not sure that will really work. Like which points? Would it be the kind of dead center of where each one lines up? In any case, maybe we could fix that, but the easier solution is to say we don't need a one-to-one representation. We can have a many-to-one. Sorry, not a one-to-one relation. We can have a many-to-one. Similar thing with the ticking clock, right? We already talked about this example, right? If we have an analog clock that ticks in discrete steps, well, then in 1 minute, we have precisely 60 individual representations. But physically, in the real world, there are many more than 60 individual chunks of time when a minute goes by. So if we talk about homomorphisms like this, rather than isomorphisms, we can make sense of the fact that we can measure time with higher resolution, right? So we could measure the exact same amount of time with a clock that measured things in milliseconds, right? So our representation has a whole lot more, it has many more pieces. Time doesn't have many more pieces. Time itself has whatever it has. Maybe it's continuous and it has a continuum of pieces. But if we allow this many-to-one mapping, then we can say, look, our representation is representing whatever it is with a certain resolution. And a clock that ticks in seconds and a clock that ticks in milliseconds, say, they're representing the same thing, even though they have different numbers of parts, right? So to put a picture to this, if we have isomorphisms, isomorphism on the left, where we have a one-to-one mapping, then we're not going to be able to talk about a ticking clock representing time that's continuous. But on the right, when we have a homomorphism, we're going to have a many-to-one mapping. We can say, look, all of this interval of time, all of these individual bits of time between 0 seconds and 1 second, they all just map to the same angle when we're talking about a clock that ticks in discrete seconds, right? So we can easily just talk about the resolution of a representation, or the same thing with the pixels in the low res picture of the Mona Lisa, right? So it's a small point, but I think it's an important point. Okay. One other thing I'll mention, there was a paper by Greg Nerschberg and Larry Shapiro a few years ago called Structure and Indicator Representations. They said it's a difference in degree, not kind. And so they argued that, so indicator relationships or indicator representations are simple things like a fuel light in your car that lights up, it says, you need gas. It just turns on or off, indicates that something is happening or not, or indicates the presence of something or its absence. It's just a kind of binary representation, right? And they said that structural representations and indicator representations are really the same kind of thing. It's just that indicator representations are a limiting case of structural representations. So they use this example of a spring scale, right? So on this spring scale here, we can imagine that we start with one where the way these work is you have the top attached to a fixed point, and then you can weigh something by hanging it on the hook on the bottom. And then the red line will go down, indicating how many newtons of force is on that hook, which is, measuring the weight of something. So we can imagine that, we start with one that just varies continuously as one normally would. But we could also imagine that, for whatever reason, we could set this up so that it kind of ticks in discrete steps. So these little markings that are fifths of newtons, maybe it can only click between individual ones, right? So it's goes in discrete steps. It has a resolution. But then, we could just increase that resolution, right? Or sorry, decrease that resolution. So now it just ticks in 2 Newton steps, right? So you put something on there that weighs 1.7 newtons and it doesn't do anything until you put something that weighs 2 newtons or more, and then it clicks to the 2 newtons level, right? Well, then you could lower the resolution still, so it's in 4 Newton steps. And then you could lower the resolution, so it's in 8 Newton steps, right? And their claim is that at this point, what we have is just an indicator representation. What we have is something that tells us if something is, or if something is greater than 8 newtons. It's basically a switch that says, yep, the thing you're weighing is greater than 8 newtons, right? And so we started with a structural representation where, it's also what I'd say, it's also a straightforward analog representation. But as we decrease the resolution in these, making these discrete steps bigger and bigger, up to the limit where we can't decrease it any further, now we just have an indicator. It's just an on-off kind of thing. It just says, yes, this weighs more than 8 newtons, or no, it doesn't, right? So their claim is, yeah, there is a bit of a difference between structural and indicator relation or representations, but it's just that the indicators are this limit case of structural representations. I think that they're right, but only sometimes. And here's why. This is my fantastic rendition of a conveyor belt at a grocery store. I should have had some robot draw this for me, but I didn't. So I'm guessing most of us have had experience with, you buy something at a grocery store and you put it on a conveyor, or the person working puts it on a conveyor, and then it goes down to the end, and there's some kind of sensor that detects, when something has reached the end, and then it makes the conveyor stop, right? So that it doesn't just keep pushing things. So we could have two different kinds of sensors, right? Let's focus on the one on the right. This is my bad version of something that kind of detects these red lines. It's meant to be a kind of sensor that detects how far away an object is, right? And just to make this most perspicuous, we can imagine that there's, say, a light that turns on, and the brightness of the light indicates how far away the object is. So as that milk carton gets closer and closer to the end of the conveyor belt, the sensor is detecting like, oh, it's, 12 inches, it's 10 inches, it's 9 inches, 8 inches, and then that light is getting dimmer and dimmer. And then when the light goes off, the conveyor belt stops, right? So there we would have a structural representation where we're representing the distance between the sensor and the milk carton, and it's getting smaller and smaller. And then when it's, some predetermined point, then it turns off. And we have a light that shows how far away the thing is. That would be a weird way to do this, but it's a way we could do it, right? And we could do the same, we could perform the same move that Nurschberg and Shapiro did, where we could say, we could imagine kind of decreasing the resolution of this sensor so that, the light, instead of getting, having 20 levels of brightness, maybe it only has 10, or maybe it only has 4, or maybe it only has 2, or maybe it only has 1. We could kind of decrease the resolution of this representation so that in the end, it ends up just being an indicator, right? Although we're detecting the distance, it ends up just saying, if the milk is less than 4 centimeters, turn the motor off, right? So that would be a case where we had a structural representation, we decrease the resolution, and we end up with an indicator representation. The other way to do it, the way that grocery stores normally do this, as far as I know, is with the green one, where we just have a beam of light, and when something breaks the beam of light, it turns the motor off, right? That could also be an indicator representation, but that's not something that we can increase or decrease the resolution of to get something that would have been a structural representation. That's just an indicator, right? When it either breaks the beam of light or it doesn't. So that's a kind of example where that's not the limiting case of a structural representation. So I thought that was a kind of interesting point that, there is still a difference between some indicators and some structural representations. It's true that you can make the resolution really, really low and have just an indicator. Another example of that would be our Mona Lisa picture. We could have a single picture or a single pixel representation of the Mona Lisa that's in black or white that just is an indicator of whether there's something bright that's being photographed or not. That would be a silly thing to do, but it would be an indicator, and it would be a limiting case of a structural representation. It'd be super, super low resolution. But things like this detector, where we just cross the beam, that's not a structural representation, and it couldn't have been a structural representation. Okay, we're about out of time, so I'll end there. Works out perfectly. So hopefully this is clear that the features of structural representation that make it interesting are exactly the features of analog representation that make it interesting. So I think that this theoretical identification can be useful, if nothing else, because structural representations typically come from cognitive science and neuroscience, whereas analog representations typically come from computation and other artifacts. And by come from, I mean, where have people been talking about these things, right? So if it turns out if they're the same thing in the end, that's useful. We might be able to apply resources from one domain to the other. And I think that going through all these motions is actually useful because, this characterization highlights that there are dimensions of variation and magnitude structures that are necessary. And that seems more useful than other ways that we might stratify different types of structural representation. Let's just focus on what are the dimensions of variation, how many are there, and what magnitude structures are there. And there's more to say here. I won't say anything here, but this also ends up applying to iconic representations. And if you know what the parts principle is, we can make sense of that. We just have to add a further complication in talking about different kinds of magnitudes that are involved. So if you're interested in this, that ends up being a difference between extensive and intensive magnitudes. But if you don't know what that is, don't worry. Okay, that's all. Thanks very much for your attention.